Welcome to the Computational Fabrication Seminar,
a web series showcasing new research, exciting ideas, and exchanging thoughts.
Our weekly 1-hour live sessions rotate through 3 different time zones and are jointly organized by IST Austria, University of Washington, and Singapore University of Technology and Design.
Each session starts with a motivational opening talk given by an expert from industry or a field related to computational fabrication, such as robotics, computer graphics, mechanical engineering, material science, HCI, applied math, design, or architecture.
The motivational talk is followed by a technical deep dive. We invite our audience to ask questions during the talks via YouTube comments and join us afterwards on Discord.
Good afternoon. My name is Michal Pivaci, and I will be the host for today. And the theme of this week is Microstructures. It is my great pleasure to introduce our motivational speaker for today, Elissa Ross. Elissa is a mathematician working in the architecture, engineering, and industrial manufacturing industries. Her doctoral research performed at York University in Toronto in discrete geometry was concerned with the structural rigidity of periodic frameworks. She has worked on problems in architectural geometry and shape modeling, including developing architecturally sensitive mesh offsetting generations for CAD. Her current research interests focus on using machine learning to predict material performance of lattice geometries. Elissa is also a partner at Mesh Consultants, a Toronto-based geometry consultancy. She is also the CEO of the 3D printing startup Metafold, which takes a mathematically driven approach to printing highly complex geometries in large build volumes. Elissa has a long history of collaborative and interdisciplinary projects and has worked with architects, geologists, designers, computer scientists, artists, physicists, and engineers. Today, her talk will be about additive manufacturing for metamaterial challenges in industry.
Great, okay. Thank you. Let me just share my screen. All right, are you seeing my screen?
Yes.
Thank you. Okay, well, thank you so much for the invitation to speak and the introduction. I'm really excited to be here today, and I'm going to be talking about additive manufacturing for metamaterials, and in particular for metamaterials in an industrial context. As a brief overview of my talk, I'll be just introducing the basic concepts of microstructures and metamaterials. And then I want to highlight the interface of those ideas with additive manufacturing, and in particular, highlight some of the challenges that come up in an industrial setting. And then I'll conclude with a kind of report on the state of the art, which is a new printer that my company Metafold is developing to print these challenging geometries. First up, though, what is a microstructure? And there are a number of different definitions of microstructures with varying degrees of precision. Today, I want to highlight two principles that I think kind of define the idea of microstructures. The first principle is that microstructures are small-scale architectures that modify the macro-scale behavior of an object. So an example here is wood and wood grains. So we're familiar with kind of the granular aspect of wood and the sort of cellular makeup of wood. And the point is that those cells, those wood grains, they fill the space of wood to give it particular properties. And you're probably familiar with this. If you cut wood against the grain, you get a certain behavior from the wood. And if you cut wood along the grain, as in a beam for lumber or so on, you get a kind of different material property. And this is a result of the wood microstructure. Similarly, bone, where many of us have seen images of scanned bone and the interior structure of bone. So bone is kind of like a natural topology optimization. The bone tissue and structure responds to forces on the bone, depending on where it is in the body, and will develop accordingly. And they'll develop this cellular structure that appropriately responds to the expected force on the relevant part of the bone. Similarly, for something like honeycomb. The second principle of microstructures that I want to mention is this idea of separation of scales. And this is super important, that the mechanical behavior of microstructures is really to be understood as the average behavior of a sufficiently large volume filled with microstructures. So it's not enough just to look at a couple of microstructures, but we're talking about a large volume filled with a great quantity of microstructures. And so this diagram here illustrates that. This is our macroscopic volume, which has a certain scale to it. This is to be understood as our microstructure. And then here we have the very fine, perhaps microscopic, actually truly microscopic scale that is, again, smaller. But the point is that this microstructure is much smaller than the macroscopic object. And this relates to the idea of homogenization, that when we are trying to understand microstructures, we really want to understand them as a material. And so this image here is from the lab of Dennis Kochman at the ETH. Here, we have a kind of beam lattice structure. This is a kind of microstructure. And when we're thinking about the mechanical behavior of this particular structure, it's really to be understood as a structure, and that we want to model each individual beam independently. But the idea of homogenization involves miniaturizing those lattice structures and increasing the number of them until we can forget about the individual beam elements and modeling each one individually, and we can replace them with a representative volume unit or just some material model that doesn't involve simulating each and every beam. So another way of thinking about this is that in this small sample here, the behavior of this chunk of material is really dominated by the boundary condition. And as we get smaller and smaller, the boundary condition becomes less and less important. And we begin to think about things like that wood example that I showed, where the wood really has this quality that emerges from the microstructural behavior of the wood grain. On the topic of metamaterials, I draw a line with metamaterials as being materials that are engineered. So it's basically observing these principles of microstructure and then turning around and actually engineering at the microscale level the behavior that we want. And so using that idea that we can control the macroscopic behavior through engineering the microstructure. And why would we want to do this? Well, in this image, this is a material property diagram. We have strength versus density. And many of you have probably seen these kinds of images. On this plot are metals, ceramics, natural materials like woods, foams, and so on. And a natural question is, how do we push into these white areas, these areas that are not covered by existing materials? And one possible answer is through metamaterials. So I would like to draw your attention to these long finger-like regions here. This one in particular corresponds to carbon fiber reinforced polymer lattice. And it begins on the dot corresponding in the polymer section, but then it extends into material property space through a variation in geometry. And that's really the idea of metamaterials, that we're using geometry. This is in the case of mechanical metamaterials. We're using geometry to mimic nature, or in many cases, go beyond properties found in nature. As a couple of examples, there are many remarkable examples of these types of materials. Just to highlight a few, though, these have been used for things like cloaking. This is a unusual unfeelability kind of structure. These are known as Pentamodes. Many of you have probably seen auxetic materials. These have a kind of a contra-intuitive behavior with a negative Poisson's ratio, and they behave kind of the opposite to what you might expect. And finally, we can also achieve things like these ultralight metallic lattices. So these are all examples of metamaterials of of materials that end up having properties that are really not found in nature. And there are many different forms of microstructures and metamaterials. And just to provide a bit of a taxonomy here, there are kind of maybe three categories that I'll just highlight, sort of cellular or random structures. These would be kind of open and closed cell foams, but also any kind of stochastically generated material. And then many of us are probably used to thinking about these slender beam architectures as lattices. This is sort of what I think of as a lattice. But then also recently, there's been a lot of interest in these smooth topologies, these things like a triply periodic minimal surface, or even not minimal, just a level surface, or other kinds of surface or plate-based lattices. And for the purposes of the rest of the talk, I'll be thinking about all of these things as lattices, as metamaterials, and as microstructures. Now, this brings me to additive manufacturing, and I thought it was funny. So when I went to propose my title for this talk, I first went to see if Jonàs had given his title, and indeed he had, and he had chosen metamaterials for additive manufacturing, which I was kind of amused to see because the title that I had selected was additive manufacturing for metamaterials. And so I actually tacked on something about an industrial context just to differentiate. But the point is that this highlights something that I want to think about a little bit, and I'm going to call it the metamaterials paradox, which is that additive manufacturing, the existence of additive manufacturing, has really pushed forward the study of metamaterials. And the work of Jonàs is an example of this, and there are many, many people doing amazing research in this field. But on the other hand, additive manufacturing has not really realized the promise of metamaterial production at scale. So many of these developments that are so remarkable and that are happening in the academic realm, it's hard to scale them up to a place where they would be relevant in industrial context. And there's lots of reasons for this. First is that these can be very complex forms, possibly with very intricate detail, and almost always have very high surface area. And another central challenge is just scale, that if using traditional methods, this involves a lot of geometry processing, mesh representation, a huge amount of computation power, and there's some computational bottlenecks involved. So if I could really boil it down to be something very simple, I would say that the current capabilities of additive manufacturing are like this. We can print very large parts, or we can print very detailed parts, but we can't print large detailed parts. And so the result of this has been that, in a way, there's been a limited uptake of many of these remarkable developments in metamaterials in industry. And we have examples like this. Many of the shoe companies have something like this. It's a 3D printed midsole. And you can see that there are several lattice elements here. But this is very, very far from realizing that length scale separation that I was mentioning that's really critical to the definition of microstructure. And I don't mean to diminish these efforts, because I think they're really important and really cool and they have their own value. But the point that I want to make is that this isn't really metamaterials or microstructures in the way that I've defined it. So in other words, the lattices that are used in industry are really lattices as structures, not lattices as materials. Which brings me to Metafold. And we are trying to address this issue by creating new software and hardware intended to print lattice materials. So we're really trying to realize that length scale separation. And this is a admittedly strange video, but what you're looking at here is actually the bottom print here on the build plate. And this is a gyroid print. So it's a triply periodic minimal surface. And we printed it at a very fine scale. This is only a 5 centimeter cube. We printed it at a very fine scale, and we're able to achieve this very unusual optical effect, which is that the gyroid actually seems like a solid. It feels like a solid mass, almost like a material, but then it has this, this optical property, which is very curious. It's almost invisible in certain light conditions. In terms of our technical approach, I won't really say too much about this here. It's a DLP-based printer. This means that we're using light to cure liquid resin. But the critical thing is that we've developed both software and hardware that interface together that allow us to print higher complexity and larger forms than other methodologies. And the kind of idea is that we only generate the geometry that we need at print time. We don't need to pre-compute the kind of closed form geometry all at once in advance and then do some computation on it. We just compute what we need at print time, and it's this feedback, this closed loop between the software and the hardware that allow us to print higher complexity and larger forms. In terms of our development status, we built our first prototype about a year ago now. That was intended to prove out our kind of complexity hypothesis. And we actually formally launched the company a few months ago after submitting some patent applications. And now we're working to prove out the scale hypothesis, which is that we can scale this up in a very dramatic way. So just to highlight a few examples of things we've printed, and this is all on our small printer. So we've printed many surface lattices. The center image, you get a sense of the scale we're working at. I think this had about 30,000 unit cells. We're able to print a really remarkable range of things very easily. So we've been able to print some more unusual surface lattices that we're not often seeing in the research. We have been exploring and having fun printing these hierarchical lattices. These are, again, have really interesting structural properties. They can be very, very light, yet very rigid because of the interplay between the macro and micro lattice. And these are very difficult to generate in standard CAD tools, which is why it's great that we've been able to just print them using our tool. And they have, again, very high surface area, which is what makes them very challenging. We have done some work printing more stochastically generated things. This was a nice paper out of the ETH, where the authors basically developed an inverse machine learning model it takes in a stress matrix of your desired performance characteristics, and then it outputs the design parameters that provide a kind of geometric prescription to achieve that particular response. And again, these forms would be challenging in standard workflows because they're implicitly defined. And we were able to effectively implement the algorithm that the authors defined for their generation, and we can just directly print them. And as our last example, we also, of course, print more beam-like lattices. The example on the right has over 500,000 beams. Again, this is on our V1 printer, so it's our small version printer. We're really excited about scaling this up so that we can print many millions of beams and many millions of unit cells. And here you get a sense of the scale of the beam elements themselves. So to conclude, additive manufacturing for metamaterial challenges. So we're really excited about the idea of creating a real option for a printer that will print lattice materials, not just lattice structures. And we're also really excited about the idea of kind of amplifying and bridging the amazing research that's being done on metamaterials and on microstructures, and being able to translate that into to industrial contexts. And of course, it's very much a team effort. And I should say also that Metafold is a spin-off of Mesh Consultants, which is a Toronto-based geometry consultancy. And that's where I'll leave it. Thank you so much. I'm looking forward to hearing Jonas's talk, and also to receiving any questions that you may have. So thank you.
And thank you as well for the inspiring talk. And I would like to remind the audience to post their questions in the chat for a joint question and answer session at the end of our talks. And today, our deep dive speaker is Jonàs Martínez. Jonàs is a researcher at INRIA interested in computational fabrication and stochastic geometry. He received a PhD from Universitat Politècnica de Catalunya in 2013, followed by a postdoc at INRIA. He's currently leading the project Muffin that aims at contributing a unified pipeline for the efficient and scalable synthesis, visualization, and modeling of additive manufactured microstructures with tailored microscopic and microscopic behavior. And Jonàs will give us a deep review on metamaterials for additive manufacturing.
Thanks. Can you hear me and see my screen?
Yes.
Okay. So first of all, I would like to thank the organizers to give me the opportunity to give this talk. I think that's a very nice idea. And also, it's been also a pleasure to see the talk of Elissa because it fits very nicely with what I'm going to show now. Especially the introduction is going to be overlapping. So just to do a brief presentation, I'm Jonàs Martínez. I'm a researcher at MFX at INRIA. We are a newly created team that revolves around additive manufacturing. And in particular, we're interested in algorithms. We are in this National Institute of Research of Computer Science in France that is called. And I'm going to give you an overview of what we have been doing the last 4 or 5 years. So, as Elissa noted, actually there are several different definitions, and myself I found sometimes having trouble to find a unique definition, but it seems that there is not an agreement on what is a mechanical metamaterial. So I'm going to stick with this definition here, which is that is an artificial structure that has some mechanical properties that are defined by the structure rather than by the composite they are formed of. Of course, there can be other definitions like materials that exhibit properties that do not exist in nature and so on, but I'm going to stick to these definitions. So it's basically materials whose properties come from the geometry, the arrangement of the geometry at the small scale. So again, this is a kind of a repetition. Different applications. One of the most well-known is Stochastic Metamaterials, for instance, to design materials expand when you do tensile stretching, which is counterintuitive. Also, I have a look at this recent paper, which is very nice on functionally integrated materials using spinoid metamaterials. So here you have an example of an stochastic material where you have different types of material properties. And then this is actually one of the parts we're more interested is in creating metamaterials that exhibit a wide range of properties while being able to print them. Another field that has been paid a lot of attention to metamaterials is topology optimization, where in the past, basically, the objective was to find, for instance, the stiffest design with some volume. But now that we can print small scale structures, we can find designs that improve because we can also control the microstructure geometry. And one of the most classic problems to find microstructures that exhibit very stiff behavior while being light. This is another application that we also have played a little lately, and this is actually a publication of us in collaboration with the scientists in soft robotics. So here, metamaterials can be interesting, for instance, to obtain deformations of a robot that are more interesting than the ones that you get with traditional materials. So for instance, on the left, you can see one gripper, I think is called, pneumatic actuated, that has some homogeneous material, and the one on the right is done with our metamaterial with some graded properties, and it exhibits different behavior. And another, this is one application among a lot because there's a plethora of them. But for instance, you can do also other things with metamaterials, such as doing shape morphing metamaterials that exhibit some interesting behaviors when you compress them, and so on and so on. So as you can see, there's a lot of possibilities, a lot of fields of applications that metamaterials show great promise. And in particular, this is because currently with additive manufacturing, we can manufacture such structures, at least in the mesoscale. Here you have an example of one of the structures that's been printed with a regular Ultimaker using fused filament fabrication. But of course, there are other technologies available, such the stereography apparatus, the proceeds layer by layer, solidification, or for instance, selective laser sintering. And I want to show these different techniques because when we are dealing with metamaterials, we don't have to never forget that at the end they are going to be printed. And this means that we have to take into account the fabrication constraints that they impose. So for instance, for fused filament fabrication, you need things that are self-supported, because of course, due to gravity, they will fall, or unless you put supports. For the stereography apparatus, you need, for instance, structures that are single connected components, and so on and so on. So you have to take these into account when you design or when you do your metamaterials. So there are two different classes of metamaterials. I'm going to focus on two that are the most widespread. The first one is one of the most used is periodic metamaterials, which are defined basically by a representative volume element. Usually it's a cubical periodic element that is repeated through space. And the advantage is that they can be very efficiently simulated, and the storage is very compact. So you can simulate with periodic homogenization, as Elissa mentioned, the behavior of this kind of microstructures in the limit. But on the other side, there are some challenges that are being tackled by researchers now, which is when you have different families of periodic metamaterials, which exhibit different topologies, you have, and then you want to do a continuous gradation between them, you have to take into account the transition between them. So this is a kind of a repetition, but I'm going to briefly pass on this. So what is periodic homogenization? Basically is you consider that you have a representative volume element that characterizes your microstructure. And then you consider that the size of this representative volume element goes towards 0. And then you consider the homogeneous material that you will get, and you get the average properties of this material. And there are several numerical tools to do that. A less widespread line of research that we got interested is the one of stochastic metamaterials. You have an example here onto the left. On one of the cons of stochastic metamaterials compared to periodic ones is that, for instance, the homogenization becomes more costly. I will explain that later. It's more involved. But one of the big advantages is that you can do grading in an implicit way. So for instance, here you have a stochastic metamaterial that grades from almost solid to almost void. And you can do a continuous grading of material properties in a more implicit form. It is not that it's not possible to do that with periodic materials, but stochastic metamaterials are even more free to do so, because basically they are not constrained to the periodic structure that periodic metamaterials impose. So how do we compute the average behavior of an stochastic material? That's actually a pretty involved question. Usually what we consider is the so-called cut-off techniques, where we take basically a representative sample of our random media, and then we try to find what is the size that gives us a good approximation. And here you can see basically these are points randomly sampled on a space. As you can see, the first window on the left, maybe it's not enough for simulation. And the one in the middle can be a good agreement. And on the contrary, the one onto the right, it's totally overkill. And so what we do usually is try to find what's the size that best approximates. The interesting thing is that actually it's been proved that when the size of this cut goes to infinity, it converges actually to a stable behavior. So coming from computer graphics, initially we draw our inspiration from something that was really old, which is procedural solids. You can see here an example from SIGGRAPH in 1989, hypertexture. And here what's going on is basically that you have a procedural definition of your solid. So basically for each point on the space, you have some lines of code that are going to tell you if it's either solid or it's empty. It's as simple as that. So as you can see, it's very compact. It doesn't involve having a mesh, and it's amenable to scale with microstructures and fabrication. Here you have another example, and you can find, if you want to have a look, you can find a lot of them in Shader Toy, procedural solids. So here's the pipeline that we will follow in all the next results I'm going to show. So just to recall from the beginning. So we have some object that we're going to fill with a microstructure in the interior. And then at some point we want to print the slice. So what we're going to do is to call our procedural code to fill the interior of this slice with a microstructure. So basically, we never generate meshes in our approaches. And people keep asking us for a mesh, but it's difficult for us to provide them because we don't generate the mesh. We generate directly the instructions for printing. It can be in the form of a G-code or, for instance, an image for stereolithography, but we never implicitly store a mesh. And also, before continuing with my presentation, I'm going to do a brief explanation of two types of elasticity that we consider. The first one is isotropic elasticity. So this is the most simple. Imagine that you have some body, and then you apply some force over it. And the force is applied to some area A. So we call the stress the force divided by the area. And then, of course, this force is going to cause some deformation. And the ratio of this deformation and the total length is called strain. And this is a relative measure. And we denote by Young modulus the ratio between the stress and the strain, which is given by this formula, and the Poisson's ratio, the ratio between the lateral strain and the horizontal one. So it's a dimensionless number. So an isotropic material is one that is entirely defined by these two constants. Intuitively speaking, this means that regardless of where do you do the compression or extension to your material, it's characterized by these two numbers. Another kind of materials that we consider are orthotopic ones. These ones are defined by more variables. I'm going to give a very brief explanation. So basically, we have an orthogonal frame, XY here. And if we apply a force in one direction, we get some Young modulus and Poisson's ratio. If we apply the same force into another direction, we will get a different Young modulus and a different Poisson's ratio. So basically, these are materials that have independent orthogonal Young modulus, Poisson's ratio, and shear ratio, which I did not enter into details, but basically is to give a notion of what means orthotopic material. So let's start with procedural foams. This is one of the main lines of work we did. And we did 3 different studies. The first was on isotropic materials. The second one is on orthotopic, and this last one is also on orthotopic, but for a different technology. So you can see here SLA, SLS, and fused filament fabrication. Because we never try to forget that at the end we want to print that. So we have to take into account these constraints, the fabrication constraints. So let's dive first into the first work. So what we wanted to do is basically an isotropic material that we could print with an Autodesk Ember, which was is this kind of stereolithography machines. And the fabrication constraints here are basically that you need to have no local minima in the direction printing. So basically, you cannot have this kind of islands. And also, you cannot have enclosed voids because they will trap the resin in the interior, and that's something that you want to avoid. So we figured out that having convex cells, a cellular structure with convex cells, it's good because then you guarantee that you don't have local minima. And in particular, an open cell structure, it doesn't have enclosed voids. So just taking the edges of a 3D Voronoi diagram seemed promising. And we dived a little bit more, and we saw that there were already several studies on Voronoi microstructures. And it's interesting because when you consider a small piece of the space, it's been shown that actually the randomness of helps to get a better isotropy for a finite extent. Also, we got interested because the Young modulus is correlated directly with the relative volume. However, the Poisson's ratio remains quite stable and positive. So how do we compute in a procedural fashion this? Basically, we have some input density field given by the user that indicates some density distribution of the seats. And then you have some point Q, and you want to determine whether it's solid or void. So what we do is recursive gathering of seats around this point, the seats of the Voronoi diagram. And we compute some local bisectors, like the local on the point Q. And then we can determine if the point belongs to a Voronoi edge or not. So we do that without never explicitly storing the seats or explicitly storing any mesh. It comes in a procedural form. So basically, we have two parameters. The first is the density of the seats, and the second is the radius of the beams. And as I said, all these operations are trivially parallel and run in constant time. So you can find 2D implementations of these already in Childertoy. However, the 3D case was not straightforward, and we had to deal with some more complex cases, but there are also implementations available. Here you can see basically a grading that shows how we grade from left to right. And finally, we also did some numerical homogenization to verify that our results corresponded to what's known in the literature. So regarding the Young modulus, as you can see here, you have the volume and the Young modulus. It correlates in a quasi-linear fashion. So it's you can encode this even with some polynomial formula. And the Poisson's ratio, for instance, here the base Poisson ratio was 0.3. So as you can see, it goes pretty stable around 0.3 and goes up to the limit of 0.5 for very low densities. And then if you put all this together, all the parameters, you get this nice plot where you can see that you have different families of Voronoi foams. And then you can also take grading curves that correspond to some Young moduli and some radius and density. Finally, something that we do also in most of the works based on cellular materials is a nice trick. It's that we can do a procedural frame also. So if we consider the intersection with the Voronoi faces, we will get this. This is a cylinder. And if we improve it, taking into account the normal, we can smooth it and we can get even a better approach. So we can do the frame of the structure also in a procedural fashion. Here you can see some really small scale structures. So I consider that these falls into the almost into the range of micro. Here another finger articulated. So basically here we're playing with different Young moduli to obtain the movement on the articulations. And here this fluffy and cute octopus that is still surviving in our office after all the compressions we did. So as you may have wondered, of course, if your relative volume goes close to 1, at some point you will start having pockets, but that's something that that you cannot escape for. So now let's go for the second class of metamaterials that we developed. And in this one, we wanted to do an orthotopic material. And this resembles a little bit to the slide of Elissa showing the wood, because what we wanted to do is a material where we can change locally the local frame of orthotopy. So basically something where we can define how stiff is in one direction and how stiff is in the other orthogonal direction. And this is because, of course, if you enlarge the space of materials and then you can adapt directionally to the loading scenarios, you can devise better designs. So our first try was to take the Voronoi diagrams and just stretch it. So if you do that, that's actually okay. But of course, this is quite difficult to compute when to lift to 3D dimensions, because either you do an inverse mapping or you compute Voronoi anisotropic diagrams, which are difficult to compute procedurally. Then we thought about doing an anisotropy point sampling, but actually it doesn't induce any orthotopy. And we even tried to, for instance, vary the Voronoi edges regarding following some direction, but it didn't work. So we wanted to take another approach, and we thought about getting inspiration of this kind of laminate-like materials. And I'm going to show you or truss materials that are following like a laminate structure. So what we did is to consider basically a k-nearest graph of a set of points. So basically, again, you have an input point distribution. And your k-nearest graph here, it's basically for each point, you're going to link it to the k-nearest closest. So for instance, you can have k equals 6, and you're going to link it to the k-nearest 6 points. And you can do that considering some metric. So in our case, we consider a distorted metric, which is basically the Euclidean one with some fine deformation. So as you can see, we have two parameters. One is the angle of this metric, and the other is the stretching factor. And finally, we also have the beam thickness parameter. And we found that this gives actually an orthotopic material that spans a pretty wide space. I'm going to enter in more details about that later. So that's interesting. There's been a lot of studies on what is the number K that guarantees almost that your network is connected. Because of course, if K is very small, you can have networks that are non-connected. So for K greater than 6, 7, it's been proved that it's almost impossible to have a disconnected network. But for instance, I can put you here a counterexample, nicely fabricated, where you get a disconnection. But this is highly unlikely, and we never encounter. Another thing that is nice from k-nearest graphs is that they are amenable for procedural computation. This means that, again, we can take a window on the space, and we can do an independent evaluation of this window in parallel without having to evaluate the whole, without having to generate a mesh, etc., and in parallel. So regarding orthotropy, we wanted to verify that actually this kind of stretched k-nearest graphs are an orthotopic material, and we pose an hypothesis that is that the metric angle translates to the same angle of orthotropy, and through numerical homogenization we have verified this. So here you have a plot where the points that are closer to the outer boundary indicates close agreement with orthotropy, and the other indicates the contrary. And as you can see, there is a close alignment with the orthotopic axis. Here, I'm going to show you the material space in 2D. So for instance, in 2D, we span a quite wide space of young moduli, almost reaching the complete square, which the complete square will be like the optimal bounds achieved by laminates, but we achieve something that it's pretty close. And here you can see some samples of this space. So basically here what you can see is the young moduli in one direction and the young moduli in the other direction. And the color, you can see that is correlated with the stretching factor of your metric. So the more you stretch your metric, the more extreme is going to get the contrast between one direction and the another. And here you can see an image for 3D, which also expand a pretty nice space. We also did tensile testing to verify that, because let's not forget that all these simulations are done with linear elasticity, which assumes that we have very small strains. So it's only valid for very small strains. So we did some tensile strain tests, and we see that there's a close agreement with the predicted one and the experimental one, at least in terms of correlation, relative correlation. We also did some compression tests, and here is when some issues arise, because as you can oversee, if you have something that is highly stretched in one direction and you start straining it, at some point you will have buckling, because the elongated fibers are going to start to buckle. So what you can see here, this sudden drop is due to buckling. We also did some compression tests in 3D, and we also saw some close agreement. So this is just to validate it. And here, there is some possible applications of our approach. The design on the left was done by a designer, and this actually was one of the inspirations of this work at the beginning. And it took him more than 100 hours of modeling. And on the contrary, with our foam, just by aligning rapidly the fibers, we can get similar results. We can also get interesting results due to the fiber alignment. Here you can see cylinders with different properties depending on where do you compress them. And of course, you can also envision that you to use these materials, for instance, to increase the resistance by aligning the fibers to the direction of pressure and so on and so on. So finally, I'm going to show you the last work on the line of research of procedural foams. And this work was also doing a family of materials that are orthotopic, but it had a difference with the previous ones, which is that we wanted to do something for fused filament fabrication printers. Basically, the printers that common people have in home that cost 300, 200 euros. And that are where the prints are also very inexpensive to do. So it's a very nice fabric thing that it's inexpensive, but on the contrary, it imposes constraints on the fabrications that are pretty strict. The first one is, again, the no local minimum constraint. You cannot deposit filament nowhere. There's some overhang angle that you need. And typically this overhang angle is bounded. So basically, if you exceed more than some angle, it will fall apart. So you have an angle of security, let's say, where you can the filament such that it remains self-supported. So there's been some work on doing structures for fused filament fabrication. Some of them are closed cell, others are open cell. We favor using a closed cell mostly because when you do the deposition, you can get a continuous path. And on the open cell, you have to jump from one to another, which will probably pollute a lot the print. And regarding closed cells for fused filament fabrication, there was already previous work of some families, but what they had in common is that they span a small range of elastic behaviors, because they were just a single family, and we wanted to have a more wider parametric family. So our first idea was, can we do a Bornai diagram that we can print with a fused filament fabrication printing device? And the answer, when you take the regular Bornai diagram, is no, because as you can see, if this is the printing direction, you have edges that violate the overhang constraint. Imagine that this is just a section. You have some faces that are going to fall. So it's hopeless. Probably it's going to be a bad experience and not go well. There are some solutions, for instance, putting soluble supports, but we wanted to avoid that. We wanted basically to print something that was self-supporting and don't do anything after printing. So we came to the following idea. We note that with Euclidean distance, we had these angles violating. And this is because when you look at the bisectors, that is the surfaces that bisect, you take 2 points. The bisector is basically the set of points that is at equal distance from the 2 points. So if you move any 2 points in the space, your bisector can take any angle. So that's why there are arbitrary orientations. But what about if we change the distance? So basically, you can measure the distance between 2 points using another metric. So one possibility is to use a polygonal distance in 2D. And here something interesting happened. Basically, what happened is that you have a finite set of orientations. You can only have 0 degrees, 90 degrees, and 45 degrees. So that was interesting. And our intuition was that maybe there exists some distance that will enforce the non-local minimum and the angle constraint. So we saw that when you use this sort of triangular distance, this was enforced. And now I'm going to explain why. But the idea behind this project basically is this: is finding a distance, a set of distances, a family of distances, such that when you do the Bornai diagram, the resulting Bornai diagram strictly enforces the fused filament fabrication constraints. So that's what it's on this slide. So I'm going to pass this. So I'm just a brief overview of what is a polygonal distance. Basically, a distance is something that measures, that gives you a number between 2 points. And the polygonal, intuitively speaking, is you center the origin of your polygon in 1 point, and the scaling factor, that's the distance. All right. So here, if you take this weird distance and you compute the bisector, you will get this bisector. And what we know is from previous work is that this bisector is actually homomorphic to a line in 2D or to a plane in 3D. So that's nice because it completely separates the 2 points. And what is very nice is that each facet of this bisector is actually defined through the interaction between 2 facets of your distance set. So here, for instance, you have this piece of a bisector that is defined by 2 parts. So what we do basically is we take a distance. We have a method to enumerate all the different angles that can arise. And we have another method to enumerate all the possible configurations of the bisector. So here, in 2D is very simple, and in 3D there are more cases. But basically, that's the idea behind this project. And once you have verified that the bisectors are always self-supported, you can also show that the Bornai diagram is, as consequence, self-supported and printable. So we did a parameterization of this family of distances. How we do it? Basically, we consider a pyramid going in the printing direction with a base and an apex. The base is parameterized by a regular polygon with K faces. And then we have different parameters that control the origin and that control the ratio of the lateral side and the distance to the apex. So basically the aspect ratio. So you see, these are basically these parameters that appear below. And finally, what we can do is we can rotate this cone, of course. So here, let's see a visual explanation. Here, for instance, if the origin in the interior is pretty fairly down, we get a 25 degrees overhang angle minimum. Here we get 45 degrees, and here this one is pretty strict, we get 65 degrees. So that's one possible parameter. We usually fix it to 45, but the user can choose it. The parameter mu controls basically the aspect ratio. So intuitively speaking, you can get either more vertical faces or less vertical faces from left to right. The parameter sigma is basically a stretching that we do in one direction. And the more we stretch in one direction, the more that the faces, the Bernoulli faces get elongated in that direction. And then we expect to get some orthotopy in that direction, anisotropy. And finally, that's the nice thing of procedural foams is that you can play intrinsically with the point side density. So that's one slice. And you can also play continuously with these parameters. So here you can see how we continuously grade from mu0 to mu1, which is from no vertical walls to almost all vertical. And that's one of the things that we like more is that we can control also implicitly the angle. So here you have a concentrical pattern, and you can see that you get a structure that is concentrical. And here you have the same, but in the orthogonal direction. And what I want to remember again is that for all these structures, they remain printable in with a fused filament fabrication machine. And again, we do that in a procedural fashion. So this is basically a program that procedurally evaluates for each point to which Bernoulli cell it belongs. So we do a procedural labeling and then also a boundary extraction. And we generate directly the G-code, never a mesh. So here, there are some examples. We can control the elastic behavior by playing with the different parameters of this family of distances. You can see the density fields that we painted manually below to get this orthopedic footwear. And then also we did a correlation of the parameters of this family of distances and the homogenized behavior, the average behavior. So what we did is a pretty standard procedure, which is the cutoff technique and taking different random variations to get the low variance of your homogenized elasticity tensor. And looking at the data, we see it seemed plausible to consider that our material was well approximated by an orthotopic material. So having this independent Young moduli and Poisson's ratios here in the free orthogonal axis. So here you can see a plot of the three-dimensional Young moduli in all the free axes. And you can see that there are different spreading families that correspond to different densities and parameters. So as you can see, we span, I will not say a wide space, but we span a continuous space of behaviors. And we can continuously transition from points in this space. So basically, that's something interesting. And we see also that there's a strong correlation between the parameters and the elastic behavior. So here you can see, for instance, the mu is correlated and sigma is correlated with it. And finally, we, like in the previous work, we did some experimental verification. And the results were fairly consistent, but I want to point out that it's actually very complicated to precisely determine what is the elastic behavior of materials made by fused filament fabrication, because there's a lot of factors impacting it. There's also the anisotropy of the layering process. This arises in all manufacturing technologies. So we observed already this anisotropy. We had different measures in the printing direction compared to the other ones, to the other orthogonal ones. And finally, compared to the most classical tessellations by planes, what is nice of this kind of stochastic structures is that they allow for very continuous gradation. So you can, since you don't have this underlying grid, you can do more smooth transitions. And you have here a visual representation. On the contrary, they print slower because the stochastic geometry. And also, if you want to achieve extreme rigidity, usually it's a better option to use non-stochastic, but regular structures that are designed to be very stiff. So here there's another example. And what you can see is basically the rendering of the G-code, not a mesh again. This is the prosthetic finger, similar to the one we did with the Borneo foams, but this one, it was more resistant to bending. It was not brittle, finally. Here you have the RC car wheel, where you have a concentric field. That could be interesting. Basically, these are showcasing some usage scenarios. And here you have the orthopedic footwear. So we have an ongoing work that is studying actually applications of different metamaterials for orthopedic applications. And they are studying several different classes of metamaterials. And one of them is this, just to point out that it has applications. This is one example that we were very satisfied. It's a prosthetic hand. This was fully printed with a regular Ultimaker. And as you can see, it was articulated by regulating the point density on the articulations and also the degree of anisotropy. What you see is basically the printing. So from our experience, it prints very robustly. But what I mean is that basically you do several prints and you always get a hand. So it's not as delicate as other technologies that from our experience require more fine-tuning. There's a high probability that something goes wrong during printing and you don't get anything. And of course, you can put a hand over it. A skin over it. All right. So you can see Google for that on YouTube, and you will see a video with different things we did. And of course, if you want to try that, we have a software that we develop in the team where we try to push our latest research. It's called ISSL. And here, if you select the polyfoam infill, what basically you're going to use the infill of this presentation, of this last presentation. And you can play with the different parameters. So now to finalize my presentation, I'm going to do to switch to a different line. I talk about stochastic metamaterials. Now I'm going to show some work we did recently on periodic metamaterials for metamaterial design. And this work revolves on an idea also of changing the metric, which is something that, as you can see, it's something that it's following all the different words. Basically, we play with the properties of the metric, and then we try to get interesting metamaterials. So in 2D, you can do periodic tilings, and you can obtain different behaviors. So for instance, you can get an isotropic behavior, like the one on the left. This circle, basically it's the stiffness, so you get the same stiffness in all directions. Or you can do orthotopic materials and you can get these two spikes. This is a nice visualization. Again, there's a problem because you have sometimes different classes. and you would like to transition between them. So it's unless you have some implicit formulation or some constraints on the boundary, this is not something that comes for free. Oops, that was reverse. So the second one is that you want to target also some specific elastic behaviors. So for instance, imagine that you're given some specific behavior and you ask the question, what is the corresponding set of tiles that will have the same behavior? And since we are in graphics, we were also interested in not only giving the designer one option, but giving them she or he different options that may have different aesthetics. For instance, to design tilings for garment, etc. Regarding boundary compatibility, it's something that it's a hot topic currently. There's quite some papers. You have different ways to tackle that. For instance, constraining the boundary between the tiles, or having some kind of implicit function that blends between one and another, etc., etc. But in all these cases, it's usually an ad hoc post-processing technique. And if it's implicit, usually the space is pretty small because it's simple implicit relations. So, well, this is mismatch again. Here it comes our key idea in this work. So now what we consider is a periodic lattice. And again, with Euclidean distance, if you get the triangular periodic lattice, you get this hexagonal Voronoi tessellation. But we thought of doing something different and change this distance to another class of distances that we call star-shaped distances. And I'm going to talk about this later, but this is a class of distances that can be compactly parameterized by a few parameters and that give interesting mechanical metamaterials. And that's basically the contribution of this work. So basically the idea is that you can compactly parameterize your mechanical metamaterial with the periodic tiling, for instance, a triangular tiling, a honeycomb, and your distance. So you see that already there's some potential. So our contributions are, we explore the space of these combinations of type of tilings and distance. And we also show that since you can grade between different distances implicitly, by interpolating between distance, you implicitly interpolate also the tilings. So here you have 3 different star-shaped distances. The colors on to the left correspond to the corresponding metamaterial. And as you can see, it transitions from one class to another in a continuous fashion. And we do that in a completely implicit way. It comes from the distance. There is no post-treatment. So what is a star-shaped distance? We define that by ourselves. Basically, let's define a compact set that is bounded with some origin in the interior, and then some minimum and maximum radial span. And this is a star-shaped set as long as the line between the center and the boundary of the set is always contained in the set. So it's something close to convex set, but more relaxed, okay? What is nice is that you can parameterize that in polar coordinates. Basically, you can have an angle and a radius, and you parameterize your star-shaped set. And you can, this is the formula, you can compute the distance basically as the Euclidean distance divided by the distance from P to the boundary. In other words, again, is the scaling factor that you need to do in the distance centered in P to touch Q. All right, so it resembles intuitively to the polygonal distance I talked in the previous. So you can do parameterizations with different things. We played with polygonal and smooth outlines, where basically we define different points of this polar function, and then we do interpolation between them. And then we stumble with the following problem. If you take the Voronoi diagram in a traditional sense, and you do the Voronoi diagram under this distance, you will get Voronoi cells that are actually made of several connected components. So here you see P, it's the green region, and there is a green aisle in the region of Q. And that's actually not good, because since we're interested in the boundary, it will lead to disconnected components of the metamaterial. So what we did, it's very simple. We resort to the classical, another alternative formulation of Voronoi diagrams, which is the growth model, where basically you have your Starship set, and then the stars scaling in isotopic fashion. And whenever and wherever it touches another cell, it stops the scaling. That. So you start scaling, and then you get that. And this is nice because by definition, your Voronoi cells now are a connected set by construction. And then the point lattices, we consider in this world three that are pretty standard in 2D, which are the diagonal, triangular, and honeycomb. But you could use other point lattices. And that's one of the main insights of the work is basically that if your point lattice and your distance share some symmetry, so for instance, here they share a reflectional symmetry along the horizontal axis, this is going to be reflected also in the corresponding Voronoi diagram. So that it's very nice because we can impose specific symmetries to appear on our mechanical metamaterial. For instance, we can impose to have free-fall rotation. And you may wonder why this is interesting. It's because, for instance, if you have a free-fall rotational geometry, it's been proved that it has an isotropic behavior. So you see, it helps us to tailor also the class of symmetry of the elastic behavior. Here you have another example. This was 4-4 rotational, 2-axis reflection that leads to hexagonal materials, 3-axis reflection, and so on, so on. So basically, as long as they share the symmetry also appears into the Voronoi network. And again, this is also the main point of this work. You can transition between different distance by just simply changing what's the distance in one region of the space and what's the distance in another region of the space. You can do that either constantly by doing a hard transition, or for instance here, guide by some fill. And you can do it because, as you can see, when you do linear interpolation of two Starship sets, this leads to another Starship set. So we have explored different combinations. In particular, we explored the free-fall rotation, which corresponds to isotopic materials, and one-axis reflection that corresponds to orthotopic. And you can download the databases from the supplemental material in ACM library. And you will have this kind of HTML database where you can navigate and you can see your structure and the corresponding distance. And we did the homogenization with publicly available code. And I think it's not here, but the code to compute the Voronoi networks is also completely open source. So you can replicate some of the results in the article. So here you have different networks. And as you can see, we can have networks with varying Poisson's ratio going from negative to positive. We can also have different orthotopic materials. So here you can see the green line are the theoretical bounds. So if you get a point outside the green line, something wrong has gone with your simulation, it means. So basically, as you can see, we cover here a pretty wide space of ratios. And most interestingly, some of combinations lead to pretty well-known networks. So this reentrant cellular structure is something that has been around for quite some time. which means that with our approach, we can transition from well-known tilings to more exotic ones. Here you have a video of what's going on when you do linear interpolation. So you can see how it subtle changes from one tiling to another. However, I want to say that you can have abrupt changes. What I mean by that is that basically, when you do this linear interpolation, you're not guaranteed that given a small perturbation, there's going to be a discontinuous change in the Born-Noisiel geometry. So here you see there are two star-shaped sets that have almost the same geometry, but there's a slight change, and abruptly there's a big change on the Born-Noisiel. So that's something to study in the future. Here you have some 3D printed results. This one is done with a honeycomb lattice, and it has an aesthetic behavior. And this one, and the one in the middle has, if you see a concentric change in the middle, that gives this orthotropy, directional orthotropy. And again, an aesthetic material. So that's going to be all. I want to thank you again for your attention. And I will be also welcome to have questions and discuss with you after.
Thank you very much for the interesting talk. And we will now start a brief question and answer section before moving to the live Discord discussion. So the first question is for Elissa. For realizing metamaterials at large scales, is the current bottleneck on the hardware side, on the material side, or on the software side?
Yeah, so I think there's been some good advances on the software side of this. I think that what has been missing, it's not exactly the hardware. Well, our solution is this integrated hardware software solution, but it's the translation from software to hardware that I think has been very challenging, that people can create geometries on their computer that they can't print, but then there are also geometries that they can't even create on their computer that they wish to print. So I think it's a bit of software and definitely the interface between the software and the hardware.
Then a question for Jonàs. For the procedural Voronoi foam project, how are the material parameters measured without having an explicit mesh? Do you print everything, or do you have some simulation meshes?
So we did some numerical simulation. Can you hear me?
Yes.
Okay, sorry. So we did some numerical homogenization. And then, as far as I remember, we also 3D printed some families of them with different random seats and the same parameters, and tried to see what was the stiffness. So that we did both. At the time, we didn't have a compression machine, so we did a more rudimentary test. But in the other two works, we did the test with a compression machine that gives you the strain stress curves and where you can estimate the Young moduli.
Thanks. And then a question for Elissa, if you can speak about it already. At what point, or do you plan to make the printer that you are currently developing available commercially and also to non-industrial partners? And what would be the price?
I'm not sure I can comment on all those things right now. So we are in a pre-commercial state, but that means that we are in the process of building custom printers, and so we're selling printers, absolutely. And if anyone's interested, we can talk about that directly. But they're custom builds because the build volumes are custom. It depends what people are trying to do with them, and it also may involve some development on our part of the software end, depending on, again, what people are hoping to print. So yes, we're pre-commercial, we are selling printers, and we do hope to make them commercially available to both industrial clients, but also, I mean, I think our early clients will most likely be in the research realm, people who are really pushing the boundaries of metamaterials exploration.
And last question for Jonàs. So with all the metamaterials, one of the assumptions is that you can homogenize the behavior and you can treat them as a single material. However, even the finer ones still exhibit quite a large macrostructure. In your experience, does the homogenization assumption hold, or do we still need better simulation techniques which could handle these materials?
Oh, that's a tough one. Well, it depends, of course. I mean, it depends on the scale of what do you print. From my experience, for instance, the one we did with Voronoi foams, they were very small scale. And there I think that the homogenization assumption, it's plausible. It's not exact, but it gives a good approximation. Of course, as you get things that are more coarse, I think that you have to take into account more dedicated simulation, and the homogenization assumption is not doesn't hold. Also, I want to remark from our experience that we don't have to forget that these are additively manufactured materials. So actually they are non-homogeneous. Usually with homogenization, you consider some ideal materials, but what we have here, it's a layer geometry, a layer material that has some bonding, that has some chemical processes ongoing, you know, so it's very complicated, and it's an online, there's a lot of research doing basically the mechanical characterization of this kind of layer structures. You get anisotropy in the direction of printing. But yes, it's a fair question. So the homogenization, from my point of view, it works pretty well. But if you want very, very precise simulation, I think you will need to simulate what you have at hand, unless it's something really, really small. And the scale, this is interesting. The scale relates a little bit of what I commented on stochastic homogenization, which is basically when you have a stochastic structure, you know, what is the size of the window, you know, that stars. Imagine that you take a random window of some stochastic thing. So basically, it's the same question I'm asking: at what size, you know, the variance of the properties starts to be low. So this is the assumption we do here. We assume some variance of the properties, and then we consider that at some size, the variance is going to be very low. Yeah.
Yes.
Hope this helps.
Thank you very much for the answers. Oh,
could I ask one question, actually, of Jonàs? I'm curious, the work that you have on the star-shaped distances and these tilings that blend between each other. I mean, this is so beautiful, awesome. And I'm sure you've been asked this question before, but what would it take to extend that into 3 dimensions?
All right, so that's a good question. I actually wanted to show something because we have a conditionally accepted paper that is extension to 3D.
Nice.
But they told us to do not show anything before the publication. So, but yes, I have. Okay, so everybody explained me to that, and we were intrigued into the extension. So you're going to see soon results on that. On the
fantastic. I look forward to reading that. Thank you.
So basically, instead of a 2D star-shaped set, it's a 3D star-shaped set, and yeah.
Cool. Great. Thanks.
Very nice. So thanks again for staying for the Q&A and also for the inspiring and awesome talks. And I would like to invite both of the speakers and the audience to the post discussion at Discord. So thank you very much. Bye-bye.
Thanks. Bye.
Bye.